Good time to start. So welcome everybody to the last IS Princeton Colloquium of this term. Today we are happy to have Stuart Bale from Berkeley, who will tell us interesting things about heliophysics, about solar physics. So Stuart got his both bachelor's degree and then PhD in 1994 at the University of Minnesota, after which he did a postdoc at Queen Mary in London. And then he has joined the Spain Science Laboratory in Berkeley, where he has been since then. In 2004, he also joined the physics, the faculty at the faculty ranks at the Department of Physics at Berkeley, and has been a director of Spain Science Laboratory as well. Right now, he's on sabbatical in London, actually. In 2003, he was awarded the Presidential Early Career Award for Scientists and Engineers for his work in plasma astrophysics. So plasma astrophysics is what Stuart is specializing specifically with a sort of an experimental view on it, on different ways to design experiments to probe things like magnetic reconnection, collisionless shocks, and many other phenomena. He's also interested in low frequency radio astronomy and has been involved in a number of space missions, one of which, Parker Solar Probe, is what he's going to tell us about today. So Stuart, please take it away.
Okay, thanks. Sorry I couldn't be there face to face. This would have been fun.
Yeah, sorry too.
Yeah, well, I'll come back. I'll come some other time. So yeah, so this talk will be maybe sweeping and superficial, but I think there's some really interesting stuff, and we're really just getting started with Solar Probe. So there'll be a lot more down the road. But basically, this is a story about the solar corona and how it turns into a wind, into a thermally driven solar wind. So this is an eclipse image of the corona. What you see is Thomson scattered white light. So you're seeing the structure of the density, the electron density in the plane of the sky above the photosphere. And if you just go to Wikipedia and drop a magnetic dipole on it, it's pretty compelling. So this nice solar minimum, solar corona. So really, I'll get to the science questions here in a couple of minutes, but it kind of goes back to Parker's solar wind model. So beyond that sort of static looking corona, of course, is a wind, a super Alfvenic supersonic wind, and this was all kind of came about as a mature or becoming mature topic in astrophysics in the 50s or so, and Parker was influenced by some work on comet tails, suggesting that there was a radial component to the comet tail that evoked the idea of a wind. And so we developed this model, the Parker Solar Wind Model, 1958, which is a really simple hydrodynamic model. It's an isothermal model, and it suggests that you can create a wind from a static corona if you have enough heat. The model isn't really right because it's isothermal. I think it's isothermal to beyond the critical point, and then adiabatic beyond that. And if you use a fully adiabatic solution, you don't get an escaping wind. So he really used isothermal model to kind of evade the requirement of having heating inside the critical point. So the model can be made to work, and it's kind of still the basis of a simple thermally driven wind model with a heating function. So the point is, I think that we require some mechanism to provide additional heat inside the critical point to make this model viable. And it's as I said here, it's structurally similar to Bondi accretion. It's zero angular momentum, isothermal, critical points, etc. So after this model was proposed, the solar wind was measured in situ at 1 AU, first by the Russian Luna spacecraft and then by Mariner 2. And so, it all started to kind of come together as a real serious problem. And it's been observed remotely as well, both by looking at Doppler dimming of UV spectral lines, which are the green dots in that curves of this panel. So what you're seeing is the wind speed as a function of altitude or distance from the photosphere in units of solar radii. And so what you see is in fast wind, where you can make this kind of observation, you see that minor ions are accelerated as a function of radius as they move away from the sun. And in the slow wind, so we'll talk about this dichotomy between fast and slow in a second here, back on the next slide. In the slow wind, what you see are you can actually image again Thomson scattered white light structures as a function of time, and you can watch them accelerate as they move away from the sun. So the slow wind is much more structured, and again we'll come to this in a second. We call these things blobs very imaginatively, but these white light blobs are seen to accelerate as they move away from the sun, and this is probably structured and trained in a wind. There are some ideas that it's separate from the thermally driven wind, and I'll show something at the end of the talk that maybe suggests that as well. So this is a kind of canonical figure that's made by Dave McComas using Ulysses data. So this shows, so Ulysses was a spacecraft that went over the poles of the sun, right? And so this is a left-hand panel is at solar minimum, right-hand panel is at solar maximum. The radial distance here on this plot is the wind speed. So the velocity of the wind, the radial speed of the wind. The color of those bars is the polarity of the magnetic field. Okay, so on the left-hand side, solar minimum, when the solar magnetic field is at its simplest, essentially, like an exploding dipole or something. What you see is fast wind over the poles. So the radial speed here is high over both the north and south pole. Whereas in the ecliptic plane, it's highly structured and slower. Okay, so we have this fast wind and slow wind. Okay, this is the second orbit of Ulysses on the right-hand side. Now it's solar maximum, and you can see that it's much more structured of the entire over all latitudes, all solar latitudes. You have fast wind embedded with the slow wind, and really what we think is happening here. So we know now that the fast, and this has been known for a long time, but the fast wind is emerging from coronal holes. So these are open magnetic field lines which are over the poles. And what happens, of course, as the solar cycle progresses is that those coronal hole boundaries get much more structured and evolve to lower latitudes. And so this really reflects a kind of a very complicated map in longitude and latitude of the coronal hole boundaries. And so, okay, so but more phenomenologically, the fast wind is fast, hence the name. It's a little bit, it has higher levels of Alfvenic fluctuations in it. So delta B over B is generally larger. And the electron or the ion temperature is generally a little bit higher than the slow wind. So, and there are compositional signatures that are different between the fast wind and the slow wind as well. I'm not going to go into that here because unfortunately this spacecraft doesn't have an instrument that's capable of measuring that with any sensitivity. So anyway, the wind is bimodal. There's fast wind and there's slow wind. We know the fast wind emerges from over the poles. The slow wind comes from is focused in the ecliptic plane. It's not clear whether it emerges from coronal holes as well, smaller coronal holes that look negligible with a UV imager, for example, or whether it originates at the tips of the current sheet. So if you look at this figure on the right, this is from a review by Strampanucci. So these are magnetic field lines reconstructed from a potential source surface model. So it's a static, current-free magnetic field model that has a boundary. We'll come back to this as well later. That has a boundary at the photosphere and a boundary at a surface above that. But you see that there are closed loops in this model. So this is constrained with real magnetogram data. So there are closed loops in the equatorial plane, lots of closed loops, and then there's open flux as well. So and of course, importantly, this is the North Pole and South Pole have different polarities. So we know that the fast wind is emerging from the open fields over the poles, and then there's this question of where does the slow wind come from? Is it just from over? Is it wind from over the poles that's overexpanded? As it fills the vacuum of space, it expands super radially, down into the ecliptic plane. Are there small coronal holes, embedded in these loops that are emitting slow wind, or is it some instability of the current sheet out here? So, for example, tearing instabilities, or are there Kelvin-Helmholtz instabilities at the interface here? Is there reconnection at the tips of these streamers? This is one of the important sets of questions. And then the other important set of questions is, what's the nature of those heating mechanisms, or that heating mechanism that provides the thermally driven wind with the enthalpy, with the energy it needs to escape the solar gravitational potential. So there are a set of ideas surrounding that. Ideas that are based on waves and turbulence. So, this nice little cartoon from Steve Cranmer in the bottom corner shows, open field emerging from the photosphere, and then the convection motion of the cells in the photosphere, launches Alfvene waves onto these open field lines. The Alfvene waves propagate out, and then somehow heat the thermal plasma. I mean, shear Alfvene waves, linear shear Alfvene waves are not very good at damping. So you have to, one set of ideas involves setting up a cascade. So maybe you have some reflection of Alfvene waves in the Alfvene speed gradient, and then the forward and backward going populations generate a cascade that eventually evolves down to small enough scales that you can have ion cyclotron heating, or just Landau damping, or transit time damping or something. There are ideas that involve electrostatic waves. So again, ion cyclotron waves could be generated by anisotropies. It could be generated by beams. There's a class of models that involve generating ion cyclotron waves at relatively high frequencies, and then those waves heat the ions perpendicular to the magnetic field, and then you have a mirror force. The mirror force can eject a wind. So there's some evidence for that as well. Ion acoustic waves can potentially do a similar thing. And then there are ideas of, kind of more coherent phenomena like reconnection and shocks. And so there's this model of, in fact, of interchange reconnection, which has, open field lines and closed field lines, meeting favorably at some points and reconnecting. So this does a couple of things for you. One is it provides flux transport, because now this field line, has hopped over to a new foot point by reconnection. And it also lets you exploit the energy that's released in the reconnection event so the magnetic energy to heat the plasma and provide that heating function. So that's kind of the class of models. And I like to show, I love this image. This was something that was just published a week ago or so by the predictive sciences crowd down in San Diego. This is an MHD simulation of the corona using current magnetograms, recent magnetograms, to predict the December 14th solar eclipse in South America. And so this is basically just spinning through Carrington longitude. So it's a static model that's rotating around. But you can see here now, the kind of structure, right? I mean, you've got all this closed field line structure, down at low altitudes, but you have all this streamer structure as well. So open field lines, clearly open field lines over the poles, right? And then when you get down into the ecliptic plane, there's a combination of what looks like open field and closed field and streamers and pseudo streamers. And so it's a very structured system. And I got to say, this is, we're heading into solar maximum. In fact, there's some flares on the solar disk, or some active regions on the solar disk now, a few flares, apparently a CME a few days ago. So we're heading back into solar maximum, but we launched, really in solar minimum. And so that happened to be a good thing because it's already complicated enough. Okay, so solar probe. So this is the slide that I stole from the Interstellar Probe people. So the idea of it goes back really to the Simpson Committee. Well, probably maybe goes back to the Russians even. There's a concept called Vulcan. But in the US, the idea of it goes back to the Simpson Committee, which in 1960 was charged by the NRC to look at space missions. So there was, we have access to space now, what should we be doing? And they came up with these three big picture missions, a solar probe, okay, which is the NASA Parker Solar Probe now, an interstellar probe, which is the folks that I stole the slide from. There's a big study going on right now to do a proper interstellar probe mission, and a mission that goes over the poles. And that mission turned out to be the ESA, the European Space Agency Ulysses mission that I showed the figure from Dave's paper earlier. So, okay, so the idea has been around for a long time and had been studied, you know, by a couple of different decadal panels and recommended. And then we finally got a start about a decade ago, actually. And so these are the science objectives of the NASA Parker Solar Probe mission as they were laid out. So basically, there are three major science objectives to study the energy that heats and accelerates the solar corona and the solar wind. So this is, you know, essentially that, you know, what's the nature of that heating low in the corona that provides the wind enough energy to escape gravitational potential. Second, determine the structure and dynamics of the plasma and magnetic fields at the sources. So this is kind of that question of, you know, what's the structure of the slow solar wind? What are the sources of the slow solar wind? Coronal holes, you know, reconnection at the current sheet, you know, something else shocks. So that's the second objective. Number three is to study energetic particle events. So those are the events that occur with solar flares, with interplanetary shocks, CMEs, etc. And then there was once a dust objective, but that was deleted. But I'll show you at the end, if we have time, that it remains as a science objective in practice. Okay, so this all flows to a set of measurements and then a set of instruments. So there are 4 instrument suites on the spacecraft. One that I lead, that we call fields. We measure the magnetic fields, electric fields, plasma waves, and radio emission as well. We do low frequency radio astronomy. ESIS, which is led by David Thomas, which is the instrument that measures energetic particles, energetic electrons and ions and heavy ions, and has some compositional capability. SWEEP, which is led by Justin Casper, to measure the thermal, a little bit superthermal plasma, thermal electrons, ions, protons and alpha particles, and it has a little bit of capability for some minor ions that we've seen, particularly when we fly by Venus. We can see some oxygen escaping from Venus. And WISPR, which is a white light imager that I guess I have a slide on this minute. That's led by Russ Howard, and that's transitioning to Mark Linton, SPI, NRL. So the spacecraft looks vaguely like this. This is the drawing of it. This is a little bit old, but it mostly has all the right features on it. So it has a solar, what we call the thermal protection system, which is basically a heat shield on the front face of it. So this is a big carbon composite cup, essentially. So it's a big piece of carbon that's shaped like a cup, and it's filled with aerogel, like a carbon aerogel. And then it has an alumina, which is a technical ceramic, an alumina faceplate on it, which we don't like very much because it's not very conducting when we're far from the sun, but it works. The spacecraft itself is down here. So this is about, you'll see a picture of it in a minute. This thing is about the size of a little bit bigger than a 55-gallon drum. You know, if I got up close to it, I could almost put my arms around it. I'd probably I'd be in trouble if I did that, but I could probably do that. So it's not that big. And we have solar panels here. So we use solar panels to generate electricity. When we're flying close to the sun, when we're in our nominal encounter mode, we stay sun pointing. And so the front surface of this is sunlit. In fact, at our lowest altitudes, we'll take about a megawatt of solar input on this surface. And the tips of these solar panels here are in sunlight as well. But everything else here is in shadow and shade and the umbra. These are radiators behind here, and then we pump water through the radiators, right? And we pull heat off the back of this heat shield and radiate it out to space. They're very efficient. In fact, at launch, we had to have the water. They're so efficient that the water was all stored in a tank in the spacecraft, and so it didn't freeze. So we could keep it heated, so it wouldn't freeze. And then when we got on orbit, we pointed these panels one by one at the sun to warm them up and filled them with water. as they were warm enough to keep it liquid. And so, why water? I mean, water has a very high specific heat. It's not corrosive, so it seemed to be the right solution for this. The spacecraft is about 700 kilograms or so with its fuel on it. These are some pictures of it. So this is in the clean room at Astrotech in Florida. So you can see here the radiators are nice and black. The solar panels. This is the third stage launcher. This is in the thermal vac chamber at Goddard, at NASA Goddard Space Flight Center. So we actually, wired it all up and cycled it up and down in heat. We couldn't provide real thermal, a real solar flux to it. We emulated the solar flux, so that's an interesting point actually, is that NASA has this kind of idea that they like to test as you fly, you say. So you really like to test things in the environment that you fly them in. In this case, we really couldn't. So there was a lot of bootstrapping in the engineering. And then this is the spacecraft in the Farron. So we launched on a Delta IV Heavy, which is a big, I think the biggest rocket that NASA uses for its spacecraft, with this custom third stage on it to get us into the right orbit. And the launch was on August 12th of 2018, so more than 2 years ago now, from Cape Canaveral, from Kennedy Space Center in the middle of the night, 3:30 in the morning. And it was pretty spectacular. So this is the mission profile. So we launched back here. So what are we looking at? So this is distance. So this was 1 AU, distance from the sun. And so you see the different perihelion altitudes. We had 3 orbits at 35.7 solar radii perihelion, and we had 2 at 27.8, and we've had 1 now at 20.4. This is where we are right about now. We have another one coming up in January, and of course these green dots here are our encounters with Venus. So the way we're lowering our perihelion altitude, the way we're dumping angular momentum, is by using Venus gravity assist. So we encounter Venus, we slow down, that brings our perihelion down to lower altitude each time. And then after the 7th Venus gravity assist, which is out here in 2024, we'll start to have perihelia down at altitudes or solar distances of 9.8 solar radii. So that's our final perihelion distance for the mission. And then, if things are working right, we hope to keep running forever and ever and ever. One thing that's kind of cool here is that this left-hand panel shows the velocity, the Keplerian speed of the spacecraft, and you can see that when we get out here to this final 88-day orbit, our Keplerian speed is almost 200 kilometers per second at perihelion, which will make us, we understand, the fastest ever human made object. I think we're already the fastest ever spacecraft, but we'll be the fastest ever human made object when we get out here. So when we go through perihelion, we're really going at a clip. It all happens really quickly. Okay, so let's talk about some data. So I'll show you data from the Fields and Sweep instruments. So Fields is the one that I lead. Sweep is the one that Justin Casper leads. Fields measures the magnetic field with some magnetometers that are back here behind the spacecraft. And incidentally, we have to heat these things. They're cold. When we're in our normal encounter mode, they would freeze up and crack apart without some resistive heating. So we heat these things with electric heaters. And these antennas, which are in the plane of the heat shield, are to measure the electric field and the radio emission on the plasma waves. They're made of a reactor grade niobium alloy called C103. So it has a solidus point up at around 2,500 or so. Our thermal model suggests that when we get to the lowest altitudes, they'll operate at around 1,300 or 1,400 C. So they'll glow. They're 1/8-inch thin-walled tubes. They're very thin-walled, kind of floppy, 1/8-inch diameter. And really the basis of the thermal design, I won't talk too much about it except for this, the basis of the thermal design is that the cross section for conducted heat along the tube is very, very small, because the wall of the tube, the difference between the inner and outer diameters of the tube is very small. So the thing really struggles to conduct heat down along along its radial distance here. And so when we put a little heat shield in front of it here, it just radiates like crazy behind that heat shield. And when we're 1,300 C out here, we're only 100 C behind the heat shield. And all of our stuff down here in the spacecraft operates at room temperature basically. And there's also this Faraday cup, which is part of the sweep payload, which looks directly at the sun too. So this thing has the similar issues with thermal design and thermal performance, and uses the same materials, frankly, the niobium and the niobium alloys. This is I'm also going to show some data from the WISPR instrument. The WISPR is a white light imager. So WISPR it's like a coronagraph. It looks down to about 2 solar radii to where it starts to saturate, and then out to where the Thomson scattering cross section falls off. So that's like maybe 175 degrees or so. So it's got a wide field in the direction of motion. So it's looking the direction that the spacecraft is moving, and then up and out of the ecliptic by, I think it's a 70-degree latitude view. And you can see here, this is an image from WISPR during the first encounter. There's a CME. So we're looking at the stuff that we're flying into. So that becomes important. It should become more and more important as the mission goes on. And this is what the family of orbits look like. So the first 3 orbits we had, this is in orbit 1. This is now in Carrington Coordinates. So this is in a coordinate system that's rotating with the sun. So this is an important point, is that we go through periods of co-rotation, which are marked green here. And then we go prograde, and we rotate with the sun. And sorry, I should go this way. We go with the sun, and then we go through co-rotation again, and then retrograde. Encounter 4 and 5 look like this. So the loop is broader. And then encounter 6, which we had just a few months ago, looks like this, with a very broad sweep in longitude. This is essentially a 90-degree sweep in longitude over just a week or so of time. So disentangling what we're seeing spatially and temporally is a little bit of a struggle, and it's going to get worse, I think. Okay, so what do we see? So the first encounter looked like this, and this is the stuff that we published last year in a bunch of papers. We had some papers in Nature, and then we had a special issue of AppJ supplements. The top panel here is the radial magnetic field. Okay, so this is really one of the telltale signatures. So the red bars here are 1 over r squared. And this first thing you see, which is incredibly striking, I think, is that the radial magnetic field is not a simple field, right? It's highly structured, and it has delta B over B inversions, order 1, right? So the field flips over on, I won't go too much into this, but on time scales of down to seconds, down to our measurement time scale, from hours down to seconds, it flips over delta B over B of 1 and then inverts radially. And in fact, what it's actually doing is deflecting. We'll talk a little bit about that. If you remove all that structure, so what we did first was try to see the global structure of the magnetic field, or the coronal magnetic field. If you remove that structure, this panel on here, so what we've done is basically computed a running mode, looking for the most typical, most probable value in an interval. You see simple polarity inversions. So these are current sheet crossings, from positive or negative polarity out to positive polarity and back. There are a couple transients, B and E here are transients, but this is a current sheet crossing. This is current sheet. This is current sheet. And you see, actually, the 1 over r squared looks pretty good. Okay, and so what we did was we compared this to a source surface model. So again, we took a magnetogram. So that's a measurement of the photospheric magnetic field, and what the potential source surface models do. Actually, I have more on this. So let me do this properly. So this is the orbit of the spacecraft, and we've plotted this is work done by my student Sam Badman. And so he's put the color here is the polarity. Blue is inward field, red is outward field on the trajectory of the spacecraft, and then colored Parker spiral field lines, so just Archimedean spiral field lines, using the measured velocity at the spacecraft as well, and propagated them out to 1 AU. So the big circle is 1 AU, and then we've taken spacecraft measurements near 1 AU from the stereo and wind spacecraft and compared them in done a comparable kind of mode calculation. And you can see that a lot of the magnetic polarity structure that you see in the inner heliosphere maps nicely out to 1 AU. And this is not done really properly because it doesn't, where fast and slow wind have interfaces, you can have shocks and compression regions, and none of that is done properly here. But the big picture here is that the field convects nicely out to 1 AU and largely maps in polarity. So armed with that, we decided to go inward. And so we took those measurements and convected them down to close to the sun to the source surface of a potential field model. So the potential field model is just again, it takes the magnetogram as input, and you can argue about the different choices of magnetograms and flux transport and magnetograms, et cetera. But essentially it takes a magnetogram as input, and then it takes a surface, a spherical surface above that at some height, and forces all the field to be radial on that surface. Okay, so what you're saying is basically this is the surface from which the wind escapes. So below that you can have closed loops, but at that surface everything is open. Okay, and if you do that, it gives you an idea of the topology of the magnetic field below you, and so what we did was look at the variable in here is that height of that source surface. Where does the wind escape from? Okay, and so you can map. This is distance again versus now it's longitude, and you can see the spacecraft comes in like this, loops around here and goes back out. So you can map that field back down to some source surface, and then below that source surface you can compare with the potential models. Okay, so you can see, for example, down here at a low source surface, 1.3 solar radii. This is 1.3 from sun center, so 0.3 above the photosphere. You know, you can clip off some of this loop here and let it escape, right? And you can clip off this loop here and let it escape. But here you haven't clipped off enough. It hasn't overexpanded enough to give you the right longitudinal structure. If you put the source up higher, now you're not going to capture any of this stuff here, right? So this is all closed, but now you've got enough superradial expansion to align with the observed magnetic field at solar probe. So we concluded, of course, which is not a big surprise, but you can conclude that this source surface is not a sphere, right? That the wind is escaping from different heights at different longitudes and different latitudes as well. But we can start to map that out. Now we can start to understand, you know, where the and this is essentially where the dynamical pressure of the wind is balanced with the magnetic field pressure of the loops.
Stuart,
yes.
What's the inclination of the spacecraft orbit with respect to ecliptic? Is it zero?
So,
is it changing?
No. So you mean to what latitudes does it dip at perihelion? It gets down to about 4 degrees south in Carrington Coordinates during perihelion. So it's relatively equatorial, relatively ecliptic, but it does dip a little bit below, and that actually matters.
But you're feeling this 7-degree tilt of the solar rotation with respect to the
yes,
right?
yeah, that's in the Carrington coordinate transformation.
Yeah. Oh, good, thanks.
Okay, so what we came up with for our first result was a map like this. So the grayscale here is basically a UV map from a UV remote sensing UV instrument. So you can see the dark regions here are the coronal holes. So over the poles you have a lot of coronal holes. This is in sine latitude. You have a lot of coronal hole open field, and you have some that are down, some holes that are down here at equatorial in the equatorial plane as well. And this is the spacecraft trajectory again, starting here, coming around, back out in this coordinate system. And now you can map these field lines from the spacecraft down to the source surface. And we can see that, you know, for the encounter, which is here, which is blown up on the right-hand side, we were really just hanging over a small coronal hole. And any magnetic field model that we use maps our field lines right down to that coronal hole. So the wind during this whole negative polarity interval here is basically, you know, escaping from a small funnel. It's just it's escaping super radially from this little funnel. It's very Alfvenic. There's no reason to think, I would say, that whatever acceleration mechanism is heating that wind is any different from the fast wind over the poles. It's just that the super radial expansion is so great that the wind is slow. In fact, it may even be that it overexpanded so much that it passed through the sonic point and then was decelerated again to become subsonic again. That some people, Mark seems to believe that.
Sure, there is a question. Jeremy?
I'm just wondering about this potential approximation. I know it's very commonly used, but
yeah,
it can't be exact, or you wouldn't get open field lines at all. So how good is it?
It's very crude. So it's a good question. So if there are any active regions on the sun at all, you know, any dynamo action really, it doesn't work very well. You know, for three, four, so we've had 6 encounters now. For 3 of them, we get really good correspondence in terms of magnetic polarity, mapping the model to the spacecraft and then out to beyond. As we get into solar maximum, I think it'll really start to fail. We'll need to use MHD, and even that is going to be pretty crude at some point, I think. It's the simplest thing, you know. It's the simplest thing you can do. It's a first order thing to do, and for encounter 1, it seemed to work pretty well. Okay, so there's that. So I think we at least could say from encounter 1 that slow solar wind does emerge from very small equatorial coronal holes. So it's not necessarily the only source. It's obviously not the only source, but it is a source of slow solar wind. So we're making progress on one of those goals. Okay, then one of the other striking things we've seen is a phenomenon that we call switchbacks. So these were observed before, actually, with in fact, now we know what to look for. We see remnants of them almost everywhere in the solar wind. But these are the large radial inversions of the magnetic field. So from delta B over B, this bottom panel is normalized B. So you see these, you know, there are quiet intervals of wind where the wind is very radial and very quiet. And then you have what we call jets or switchbacks. And the reason we call them jets is because they're accompanied by a little pulse in the radial velocity of the plasma. So this is the wind, the solar wind itself is accelerated a little bit, or is pulsed as a jet in that interval. They're very Alfvenic. Sometimes compressible at the edges. There are compressible fluctuations, but they tend to be pretty Alfvenic, and they occur on every time scale. So this is an interval of data. This just shows you the radiomagnetic field during co-rotation. So here, this interval here is basically we're hanging over one point in the sun, about 10 degrees off in latitude or in longitude, and from the foot point, the magnetic foot point. So this is just basically the superradial expansion, and we see these things blowing past us. So we think that they're embedded in the wind or propagating in the wind, and they're just blowing past the spacecraft. If you look at the dynamics of these switchbacks, of these Alfvenic inversions, this is from a paper by Thierry Deductivit. He looked at the waiting time of an inversion and the residence time of an inversion, and there seems to be really no characteristic time scale or even a characteristic magnitude. They occur on you know, from tens of seconds down to you know, an hour or so. We see these things. So one of our major questions is, what are the switchbacks? They also very field aligned. This is from a paper by Tim Horbury, and if there's a follow-on paper by his student Ronan Laker. And Tim just looked at kind of the crossing of these things in the spacecraft frame, trying to understand, you know, their topology, and assuming some geometry, just basically assuming a cylindrical geometry, a field-aligned cylindrical geometry, which has been verified more or less by Ronan Laker. You can get. We think that these things have, you know, aspect ratios of you know, 50 to 100 or so, and they're field aligned structures. So I think I'm going to skip this because I'm going kind of slow. Also the strahl. So the superthermal electrons that are field aligned superthermal electrons, basically the coronal electron population that we observe, the strahl, seems to follow along the switchbacks in a way that suggests that they are just kind of S-shaped inversions of the magnetic field. Okay, so there's not a kind of a reconnection signature or anything. It's really just an inversion of the field, and if you sample it through the inversion, the strahl population follows that inversion. So that's another clue, I think. So there are some ideas about this. You know, are they shear flows? Is there some kind of fast ejecta that's twisting the field around? We don't think this is the case because the velocity perturbation that we see doesn't precede or come after the inversion. It's associated with the inversion. And in the end, what we think that is we think that these are basically large I think these are basically large Alfvenic structures, Alfvane waves, basically, and so they're propagating at the Alfvane speed. And so when they invert, it moves the proton population around that Alfvane speed, which is different than the wind speed itself. So John O'Squire and now Alfred Mallard as well have some nice work on suggesting that these switchbacks are simply large nonlinear Alfvane waves that are created. The inversion itself is created by a kind of conspiracy between WKB propagation, so conservation of wave action, and the fact that they're largely incompressible. The total field is constant, so the tip of the magnetic field is constrained to move on a sphere, and the fact that the background field B0 is decreasing as you go out. So delta B over B is increasing by wave action. The field is forced to stay on the tip of a sphere, and the size of that sphere is getting smaller as you move outward. That essentially gives you an inversion. In some cases, there's some more constraints to it. But this is kind of, in fact, this is my favorite model for what the switchbacks are. But another idea is that they may be, some remnant of jets. There are UV observations and white light observations of structure, small structure, low in the corona that look like little jets, ejected from the chromospheric network and macrospicules, and the timescales of these things are kind of consistent with what we might see in a typical encounter. And so there are some ideas about that. We haven't been able to nail. There's been some work looking to try to use the measurements at the spacecraft as kind of a coded pulse and correlate it with other features on the disk using remote sensing measurements. That hasn't been successful yet, but I think it's still an interesting line of inquiry. Okay, now I'll say a little bit about kinetic stuff. We see waves. We see lots of waves. We see ion cyclotron waves, very nonlinear ion cyclotron waves with strong electric field components. They seem to be associated with proton beams. There's electrostatic structure, there's electric field structure associated with them, and they're really ubiquitous, especially in the wind that looks like it's kind of quiet wind without the switchbacks. The wind that you might think is like a Parker, thermally driven wind is loaded with ion cyclotron waves, and it's also loaded with electrostatic whistlers and with Bernstein modes. So these are presumably driven by the electron population, the electron strahl, or some interaction between the strahl and the thermal core electrons, I think mediated by current balance, is generating these waves, and these are probably related to the scattering of the strahl to create a more isotropic population. And we see heat flux instabilities as well, and I think this is really interesting. I've had interest in this for a while. In particular, so the bottom panel here shows you the red set of dots is a normalized measurement of an instability, a heat flux instability threshold associated with an anomalous cyclotron instability. So this is what's called the fan instability. And the blue curve is the measured heat flux. It's normalized, but it's the measured heat flux. And what we see commonly is that when the measured heat flux exceeds this fan instability threshold, we generate a lot of narrowband whistlers and Langmuir waves together. I think this is one of the interesting results. And so this is telling us something about what regulates the electron heat conduction in this environment where it's much less mixed and perturbed than at 1 AU. Okay, finally, I want to talk about the last encounters. I think I'm down to the last 10 minutes here. Okay, so encounter 4, we went down to 27.8 solar radii, and now we're starting to see the streamer structure itself. We're starting to fly through the actual, instead of just hanging over coronal holes, we're actually entering that, seeing that current sheet flying through the streamer structure around it. This shows you the plasma density as a function of this is a function of time, but At the center, right around here, we're at about 27 solar radii. And we see this kind of periodic density enhancements that lead up to a large density interval, which is basically, I think, the heliospheric plasma sheet. And associated with these things are like sawtooth sort of velocity structures. And then eventually we hit the current sheet here and become inverted. And we can actually start to look for these things with the white light, because these are density enhancements, right? So these are, these may show up as in the white light, the Thomson scattered white light images.
Stuart, there is a question as to, can you remind us, please, what is the Alfvenic radius of the solar wind? Is it like...
The Alfvenic radius, so we don't know exactly, but we think it's a very good question. We think that we haven't hit it yet, and we've been down to 20 solar radii, although we've been very close, I think. So we predicted, 15 solar radii, something like that, which is kind of what drives our low perihelion distance of 10.
So eventually you will cross below that.
Yeah, I mean, that's kind of one of the big goals here is to get below that Alfvenic point, that Alfvenic surface. So we're in the kind of the corona, as it were, in the sense of angular momentum, there's a discontinuity there. That's the corona.
Okay.
But we're not there yet. I mean, I've seen some data that look like we're very close, but I would say nothing unequivocal. Okay, so there's density structure, and this is WISPR data, the white light imager. And so what you're looking at here is, I'm going to run in this movie. It's a movie. This is a kind of an elongation map. So we're looking out in angle from, so the sun would be down here, well, actually down at 0 degrees, and we're looking out and in the plane of the orbit of the spacecraft. So this has been transformed into that coordinate frame. And so what you'll see when I start this up is structure moving out like this. And what you can do then is integrate in some set of latitude angles. You can choose some latitude angles and integrate over this to create a time series of white light in elongation angle, okay, which is what we call a J map. And then in addition, if you assume a Thomson sphere, Thomson surface, you can measure distance on the Thomson surface as well. And so let me run this thing. It might not run very well here. And I don't know if it's maybe a little jumpy. I can step through it if it's too jumpy. Let me try to step through it. So basically you can see structure moving out away from the sun, white light structure associated with the streamer belt. By the way, all those little spiky things that you see, those little tracks, that's all debris. Here, there's a CME. You can see the core of the CME. And all those tracks are essentially debris from the spacecraft associated with dust impacts on the spacecraft body. So this dust is hitting the spacecraft, and junk carbon fibers probably are flying off the spacecraft, which is the thing we worry about. And I see Jamie's on here. Jamie was about to say that too. There's the Milky Way moving through. Okay, so what we've done is compute what we call let's go to the next slide. Boy, if the clock runs out here. So this is a time series again, those same blobs. Now I've normalized to R squared. So you can bring out those blobs a little bit in the sawtooth velocity structure. And now we can start to see, so this is the distance on the Thomson surface. Okay, and the intensity here is basically the white light intensity. So each one of these slices, vertical slices, corresponds to an integration through that movie or a similar analysis. And so the structures that are moving out like this are the white light structures. And they have speeds. If you just take the boundaries of some of these things, they have speeds that are a few 100 kilometers per second. Basically, these bars down here are the speeds that are computed from those crossings. So I think we're starting to see some of the structure. And this curve up here, of course, this is the spacecraft distance from the sun. And the width of these bars is the density at the spacecraft. So some of this structure corresponds to things that we're actually seeing in the white light and then flying through, hours later. So I have some ideas about what this means, but we're not. I think what we're seeing actually is the heliospheric current sheet being perturbed by and pushed laterally over the spacecraft by some structures below, CMEs or magnetic cores associated with a tearing instability of the current sheet, something of that nature. And there's more evidence along the associated with this, but it gets to be a kind of a whole talk in itself. So large-scale instability of the heliospheric current sheet, I would argue. Okay, finally, dust. So this is some work that's done by Jamie Soleil and David Malaspina and Brent Page and a few others. When the dust particle, a fast dust particle, hits the spacecraft, it ablates and it releases a charge of electron or a cloud of electrons and ions, and so that produces a kind of millisecond time scale voltage pulse on the spacecraft body or the antennas. And we can measure that. So we have these electric antennas. We can measure the voltage of the spacecraft at 2 megasamples per second. We see these things very clearly. We can identify them with dust. We have some statistical way of counting them up. And so we can look at them as a function of radial distance from the sun, or longitude or latitude even. So these are some figures. And we've done some work. Brent Page has done some nice work to convince ourselves that this is really what we're seeing. In particular, by looking at times when the spacecraft rotates around the sun line, and seeing the impact rate on the different, and the sign of the voltage on the different antennas in that plane. So we can actually say something about the face of the spacecraft that's being impacted, an impact rate on that face. And Jamie has done some very nice work comparing the radial profiles of that. This is published from Encounters 1 and 2, I think. The radial profiles of that count rate of dust impacts with different models of interplanetary dust, in particular with the circular orbit, prograde, retrograde circular orbits, and with the beta micrometeoroid model, which is, at least until this last encounter, I think what we believe we're seeing is dust that's been processed so much low in the heliosphere that it's broken up to where the radiation pressure can eject the dust from the heliosphere on these hyperbolic orbits. So and there are some surprises, I think, in the last encounter, and we're waiting for the next encounters data, but we're able to say something, I think, interesting about the dust, in spite of the fact that we had to cross it off the list. I won't get to this because we don't understand it quite yet, or maybe Jamie does, but I don't. Okay, so finally, in summary, so I think the data sets are really a gold mine. It's just, the instrumentation is beautiful. It's spectacular. So we're starting to say something interesting, I think, about the origin of the slow wind. We definitely see slow wind coming from coronal holes. I think we're seeing large scale structure of the heliospheric current sheet, which may be a source of solar wind as well. We see a lot of kinetics that are probably going to tell us something important about the actual heating function below the sonic point. A major point is that the solar wind at these altitudes is not like what you see at 1 AU. At 1 AU, it's so processed, it's so evolved by convection and interaction that you really just see turbulence, right? Okay, if you're interested in turbulence, it's great. You see some, there is some pulsive structure, there are rotating interaction regions. But at these altitudes, we're seeing, what looks like a magnetosphere with structure on it, the structure that eventually becomes the turbulence that we see at 1 AU. So there's a lot to do here. We need to understand these switchbacks. Are they one of the important factors in solar wind heating, or are they just a diagnostic of something else? And there's the dust too. There's more too. There's radio measurements that we have. There's a lot to say, but that's my time. So thanks.